this video, we discuss a topic called isomorphism of graphs, which helps us determine which graphs are fundamentally different from one another and which ones are basically the same. For example, when we talked about trees, we remarked that you can pick any vertex of a tree that you want and draw it as the root. This then determines which vertices are parents to others versus children. But since you can pick any vertex to be the root, that might change whether vertex 1 is a parent versus child of vertex 2 and vice versa. So in general, what properties of a graph are actually dependent on how we elect to draw it, and what properties are actually more intrinsic and depend only on the presentation as a set of vertices and edges. So for example, the following two graphs on a technical level are different. The one on the left has a vertex set A, B, C, D. The one on the right has vertex set 1, 2, 3, 4. Since those are different sets, because they have different elements, they are different graphs. But they kind of look obviously to be the same. There's a central vertex connected to three others. So are they really different, or in some way are they the same graph? Well, what about this one here? If you compare this graph to this one, as sets, they are the same. There's a vertex C connected to A, B, and D. There's a vertex C connected to A, B, and D. The fact that we didn't draw this somehow located in the center of the other three, does that really matter? Does moving vertices around in a drawing actually change anything about the graph? What about this one here? If we compare these two graphs, visually, there's still a central vertex connected to three other ones, a central vertex connected to three other ones. They have the same vertex set, 1, 2, 3, and 4, but the edge sets are definitely different. Here, for example, vertex 1 is connected to vertex 3, and here it isn't. So are these two graphs fundamentally different, or is the fact that we simply moved vertex labels around not really important? So, is the overall structure being the same something that we can actually describe in mathematical terms? And that leads us to graph isomorphism. The way that we express two graphs having the same structure or same shape, same iso, shape, morph, this is an invented word, isomorphism, they have the same shape. So if we have two graphs, G1 and G2, comprised of vertices and edges V1, V2, E1, E2, respectively, suppose we have a function that maps one graph to the other in a way that bijectively maps vertices to vertices, edges to edges, and in fact, if I have an edge in the domain graph, which connects two vertices in the domain, then that image in the range graph must connect the same two vertices images in the range. So if two vertices are connected by an edge in the domain, and then I apply this function, the function maps two vertices to two vertices, and it maps an edge to an edge. To be an isomorphism, it must specifically map the edge connecting two vertices to the same edge connecting the same two vertices over in the range. So what it does, it relates vertices and edges in one graph to vertices and edges in another, and it very precisely preserves exactly which vertices are connected by which edges. If there exists such a map, if it's possible to construct an isomorphism between two graphs, we say the graphs are isomorphic. So let's take a look at how isomorphism of graphs interacts with degree lists, just writing out a list of the degree of every vertex. So the degree list was just this list of numbers, usually either in increasing or decreasing order. I tend to use decreasing order, which lists out the degrees of every vertex in a graph. Now suppose two graphs are isomorphic. There is a way to exactly map vertices and edges between them that preserves the structure. Since connections between vertices are preserved, if a given vertex has a degree d in the domain, then its image must have degree d in the range, because the edges that connect to that vertex must be mapped exactly to edges that connect to that vertex. So if two graphs have different degree lists, it's simply not possible for them to be isomorphic. If two graphs are going to be isomorphic, one vertex must be mapped to another vertex of the same degree. So the degree list of the domain graph must be the same as the degree list of the range graph. However, this is not actually a sufficient way to check for isomorphism. It's possible for two graphs to have the same degree list but not be isomorphic. So this does provide a quick way to verify that two graphs are not isomorphic. But comparing degree lists does not tell you if they are. Let's take a look at an example. So let's show the following two graphs from earlier slides are in fact isomorphic. Okay, we had these two graphs up earlier. They clearly look the same. So our goal is to construct a bijection between the vertex sets that automatically induces a bijection between the edges that connect them. So let's not overcomplicate things. Let's just define that the function f is going to map exactly as it appears. Vertex A gets mapped to 1, vertex B gets mapped to 2, C to 3, and D to 4. So this is a bijection between the vertices A, B, C, D and the vertices 1, 2, 3, 4. Now we need to map the edges. Well, there was an edge connecting AC. Since A got mapped to 1 and C got mapped to 3, we'll map this edge to this edge. So the edge AC gets mapped to the edge 1, 3. Similarly, B and C were connected in the domain, and we can also connect them in the range. So the edge BC is mapped to 2, 3, and similarly CD gets mapped to 3, 4. This induces a bijection between these three edges and these three edges. And what you can verify is, since A and C are connected in the domain, 1 and 3 are connected in the range. These edges connect the vertices that were mapped. A got mapped to 1, C got mapped to 3, the edge connecting AC got mapped to the edge connecting 1, 3. And this is preserved for all connections in this graph. So we have constructed an isomorphism between them. Therefore, the two graphs are considered isomorphic. They have the same structure. Another example, show the following two graphs are not isomorphic. Okay, this looks a bit more complicated. There's more going on. Okay, but can we somehow see that there is a fundamental difference between these two graphs? Well, they have different degree lists. The one on the left has two vertices of degree 4. This vertex C has 4 edges connecting to it. This vertex G has 4 edges connecting to it. However, over in this graph, there's only a single vertex, 3, that has degree 4. So if we were going to construct a bijection between them, where does the vertex C go? Well, since it has 4 edges coming out of it, it must go, if there is an isomorphism, to a vertex with 4 edges coming out of it, and the only choice is 3. But then there's nowhere to map G, since this map has to be a bijection. If C is mapped to 3, then G can't be. But since G has 4 edges coming out of it, it must get sent somewhere with 4 edges coming out of it, and there's nowhere else. So there is no way to bijectively map vertices between these two graphs that preserves the edge structure between them. There are other techniques for showing two graphs are not isomorphic. Okay, degree list is the most straightforward. But suppose one graph has, for example, a cycle of a given length. So there are, for example, maybe 3 vertices. On the left, for example, A, B, C. I can make a cycle A to B, B to C, C to A. If there were an isomorphism, this would have to get mapped to 3 vertices in a cycle. Wherever A goes must be connected to wherever B goes because this edge is here. Wherever B is sent must be connected to wherever C is sent because this edge is here. Wherever C is sent must be then connected to A because this edge must go to its appropriate place. So since there is this triangle here, there must be a triangle over here. Now in this case, I could send it here. Here's a nice triangle, or here. Okay. But notice that over in this map, there are actually 2 distinct triangles that share an edge. There's no such structure over in this map. Whatever 5, 6, 7 is mapped to has to be a triangle, so the only way I can put 3 vertices in a cycle over in this map is ABC. So looking just at triangles or cycles of 3, 5, 6, 7 in some way has to get mapped to ABC. But then the edge connecting 6 and 7 has to be part of a different triangle, which means one of these edges would have to be part of a different triangle, and it can't be. So that's another way you can see these aren't isomorphic. Okay, degree list is very quick to check, but if two graphs have the same degree list, you might have to look more specifically at things like, are there cycles of a given length, how many, how do they overlap, and so forth. Okay. Another property of these two things, the one on the left has a simple cycle of length 5, A to B to E to G to C to A. Okay. 5 edges, 1, 2, 3, 4, 5, that close up on themselves. There is no 5-edge cycle over on this map, on this graph, I'm sorry. So again, lots of ways you can check by comparing how many cycles of different lengths are there to see whether two graphs are or are not isomorphic. All of these techniques, by the way, quickly tell you that they might not be isomorphic. But suppose you check degree lists, you look for cycles of length 3 and you look for cycles of length 4. If all of that somehow seems to match up okay, unless you actually have the isomorphism in hand, we don't have any results that tell us this definitely is isomorphic. We're only coming up with ways to quickly say that they are not. Isomorphism induces a sort of an equivalence relation. Okay, we have to be a bit careful with how we would formally define this. But if I say isomorphisms of graphs, in other words, I relate two graphs if they are isomorphic to each other, that makes an equivalence relation. What we have to be careful about is how we can describe the set of all graphs, because graphs, remember, have a set of vertices and a set of edges. And there were no real restrictions on what sets we could use. So if I just sort of blindly declare the set of all graphs, we're getting really close to talking about the set of all sets. And that would run afoul of the axiom of regularity, as discussed many units ago. So why is this an equivalence relation in a very loose sense? Well, any graph is isomorphic to itself. If I just put down the identity map on the vertices, I've bijectively mapped vertices to vertices. And then I just map edges to themselves, so I've mapped edges to edges bijectively, and I've preserved connections because I didn't do anything. So any graph is isomorphic to itself. In other words, this relation would be reflexive. Suppose I have an isomorphism between two graphs. Since this function has to be a bijection, it has an inverse which is a bijection. And what you'll see is that if you can map vertices from graph 1 to graph 2, that preserve edges, I can just go backwards and map the vertices from graph 2 back to graph 1, which also preserves edges. So if G1 is isomorphic to G2 by the function f inverse establishes an isomorphism from G2 back to G1. In other words, this relationship, are two graphs isomorphic or not, is symmetric. And finally, the composition of two bijections is a bijection. So if G1 is isomorphic to G2 and G2 is isomorphic to G3, by composing the two isomorphisms together, G1 is isomorphic to G3. AKA, two graphs being isomorphic is a transitive relation. So altogether, saying two graphs are related if they are isomorphic is a reflexive, symmetric, and transitive way to put a relationship between graphs, which makes it an equivalence relation, with this hanging asterisk about specifically how we describe the set of all graphs. But loosely speaking, okay, we can talk about isomorphism as an equivalence relation on graphs. So can we, what is called, classify simple graphs? So graph isomorphism is why it's actually considered acceptable to present a graph without labeling vertices. How we label the vertices is not really important in most cases. Okay? What only really matters is which vertices are connected to other ones and the cycles and paths and whatnot that are created. So if you draw a graph with no labels on the vertices, all you're really saying is any graph isomorphic to this one would be fine. The specific labels on the vertices are not really important to what we're going to discuss. So how many distinct types of graphs is it possible to draw? If multigraphs are allowed, okay, as long as you have at least one vertex, you can actually draw lots and lots of things. For example, a single vertex with 4 loops attached is not isomorphic to a single vertex with 3 loops. Since there's a different quantity of edges, there is no isomorphism between them. So even with one vertex, if you're allowing multigraphs, A single vertex with no loops, with one loop, with two loops, with three loops, and so forth, none of those are isomorphic to each other. So even with a single vertex, there's infinitely many different equivalence classes under that equivalence relation of being isomorphic. Okay, so if we have multigraphs and we ask just how many equivalence classes are there, infinitely many, just immediately. So these two graphs are not isomorphic, and you could continue this picture. But suppose we're not talking multigraphs, we're talking simple graphs. So between two vertices, you can draw at most one edge. Maybe then it's possible to actually describe all of the equivalence classes under the equivalence relation of isomorphism. That sort of problem, where you have something you've defined, in our case graphs, and then you define an isomorphism between objects in this collection that somehow says the important properties are what's preserved by this isomorphism, while the specific labeling isn't so important. And then you ask, how can I describe all possible different structures? That's called the classification problem. Can you classify or describe or list out all the different equivalence classes under isomorphism? Let's take a look at simple graphs on three vertices. Okay, so below we will actually present all possible simple undirected graphs on three vertices up to isomorphism. In other words, they are the equivalence classes under the equivalence relation of isomorphism. We're not actually going to prove that this is exhaustive, but you can try to construct any possible simple undirected graph, so the edges do not have direction, and you're not allowed to draw multiple edges between two vertices. But if you only use three vertices, you're going to come up with one of the following pictures. Either three vertices with no edges, two of the vertices are connected by an edge and that's it, this sort of structure with two edges, or three edges. If your graph has 0, 1, 2, or 3 edges in it, and you have a simple undirected graph on 3 edges, you are going to be isomorphic to one of these four pictures.